Hi friends, hope you guys have been enjoying my Fortran tutorials. Today we start with lecture 4 and today I'm going to discuss do loops, and then at the end of the tutorial I'm going to use do loops to solve a problem involving the Newton Raphson method. So essentially we are going to find the roots of a nonlinear equation. I'm Dr. Ganguly. So let's start with the basic definition of the do loops, and essentially you have something known as a do continue statement in classical Fortran. And here what you do is that you read a number, let's say this number is n, and then you have the do loop here. So you essentially have the do statement. There is a number here. This number doesn't just have to be 100, it can be 101, 105, anything like that. It's essentially a number which tells the program that it has to go here, and then the continue statement is here. So this forms the complete do continue statement as is used in classical Fortran. Now what happens here is that inside the do loop the number I will vary from 1 to n, and essentially if you do not specify something else after this n, it's going to go up by a value of 1. So the implicit increment in Fortran is 1. And so in this simple code, it simply prints out the value of I here. So we can check how this particular do loop works. So let's put it in the compiler and try to run this code. And here I have run it for the case of n equal to 5. And so you can clearly see that the code goes from I is 1, 2, 3, 4 to 5. So it will basically go from the value at which I starts to the value at which I ends. So this is the basic do continue statement in Fortran, and very often if you are looking at older codes in Fortran you are going to see the do continue statements. One of the issues of course about the classical do continue is that you have this numerical identifier, and sometimes there is confusion because in case you use this somewhere else also the same value, you may encounter problems. So in the newer Fortran codes, you will see that people essentially use the do Enddo statement. And this is more compact. You no longer have to use that identifier here. And in this code, you clearly see you go from do I is 1 to n, you print I, and then you undo. So let's try out this code. So again, the same code here in the compiler, and I have given the number n equal to 5. And I have obtained the outputs 1, 2, 3, 4, 5. So essentially you can see that the undo statement I would say is more compact and it's something which is less prone to bugs and so on. So we are going to use this in the rest of the course. Now let's try to create a more useful program using the do loop and combine it with the if then else type of statements. So what I'm going to do here is I'm going to give a certain number n, and then I'm going to print the numbers which are divisible by 13 all the way from 1 to this value n. And I also want to calculate how many such numbers are there. So the code which is given here basically reads this number n, it sets k equal to 0, and then it creates a do I is 1 to n and undo. And within this particular do loop there is also the if then else statement, or rather if then statement. And here what I'm checking is that the remainder of dividing this I by 13 should equal 0. In that case, I print I, because if the remainder of this number divided by 13 is 0, then it's going to be divisible by the number 13. And in case it gets inside the if statement here, I increment k by 1. So this is the way you increment numbers in Fortran. It is k equals k plus 1. That is the classical and I would say simpler approach. In languages such as C, they came up with k plus equal to 1, but this is how it works in Fortran. So essentially here you have a situation of a do loop, and inside that there is an if then and if statement, and at the end I print out this value k, and there are k multiples of 13 between 0 and n. So let's check this code out. So we put this program in the compiler, and then I run it with the number n is 100, and you can clearly see here that it is essentially going to give me the multiples of 13. So you have 13, 26, 39, and so on. So again, this is like a table of 13, a multiplication table of 13. And you can clearly see that there are 7 of these numbers here. So that's also coming out at the end. That's the number k here, and k is being calculated as 7. So there are 7 multiples of 13 between 1 and this value here. So this is again an interesting use of Fortran in doing simple math calculations. Now, you don't have to just increment by 1. You can increment by 2, for example. So let's say we want to write a code which prints out the positive even numbers. In that case, I would have a code like this. So essentially, this would go from I is 2 to n, and each time it would increment this 2 value by 2, and then it's going to print I here. So hopefully this code is going to print out the even numbers 2, 4, 6, and so on. So let's try this code out, and I have tried it out here with n is 11, and what I have got here is 2, 4, 6, 8, 10, which is what you would expect. So again, you can see here that the special case which is there where this 2 is simply equal to 1, the increment, in that case you don't have to put that number, but in case you have something else, you can put a number here and run your code. Now let's do a simple problem again, and this is a problem involving the sum of n numbers. Now the sum of n numbers would be 1 plus 2 plus 3 all the way to n. And so to do this, I would read the value of n, I would put sum equal to 0, that essentially starts off the program. Then I create a do loop of I is 1 to n, sum is sum plus I, and do and print sum. Now here of course I am summing a real number with an int, but I know that when I do these kind of problems, the real plus int is going to be converted to real. So I don't have to worry about that. If you are very fastidious, you could write it as float I here. Now let's check out this in the program or in the computer. So I pasted this code here, and I am essentially running it with n is 100. So this is a pretty big number. Now do loops are mostly used when numbers get pretty big, like here, and here I get the output to be 5050. Now if you know the formula for summing n numbers, you will know that it's going to be n plus 1 by 2. This is something which is attributed to Gauss, and you can prove it using various methods. I think I have discussed this in one of my math question banks, and so you can clearly see that this code works out very well here. Now in case you think that only positive increments are possible, that's not so. You can even go in a situation where I is n to negative n and basically decrement it by 5. So every time it's going to subtract 5 out of this n value, and here let's print this I and see how this goes. So I have put this code here, I have run it for n is 10, and as you would expect, it starts off with 10, then it subtracts 5 from that, so you get 5, you get 0, negative 5, and negative 10. So again, this is the possibility which is there in some situations. If you are interested in creating a series like this, then the option is to go for a decrement. Now one more possibility is that you could actually start with a negative value. So I could start from negative n and go to n, and you could increment this by 2, and let's print I to see how this goes. So essentially in this kind of situation, if we put n is 5, what it's going to do is going to start from minus 5, because I started from minus n. So minus 5, then minus 3, then minus 1, all the way to 5 here. So it is taking negative 5 and then it is adding 2 to it each time, and we are getting this series here. So there are a lot of things you can do as far as the do loops are concerned using this particular nomenclature. And now what we are going to do is let us try to solve a more realistic problem. Let's try to put this do loop and if statements to good use by trying to write a simple program to solve an equation using the Newton Raphson method. Now, of course, you know that if you have a typical equation of the form fx is 0, this is a nonlinear equation, then the Newton Raphson method says that you can find the value of x by iteratively solving this equation here, that is xk plus 1 is xk minus fxk by f dash xk. Now you start off with the value k is 0, so that's the initial guess. So you need an initial guess to start off the Newton-Raphson method. But after that you are going to proceed further. You are going to get x1 from this equation. Then using x1 here you are going to get x2 and so on. So after some time hopefully you are going to converge. Now if you are interested in the derivation of this formula, I have done that in Math Question Bank 5, where I have taken this equation in red, that is y is 3x minus x9, and I have solved it using various numerical methods, and also there is an exact solution for this. You can get it using the Lambert W function, but many a time you may not have access or knowledge of the Lambert W function, and in that case you may want to use a numerical method. Now that's where Fortran is actually most useful. So the first thing of course we do is we need f dash for our program, so we calculate dy by dx, and this is 3x log 3 minus 9 8x. Again, if you are interested in this derivative, Math Question Bank is where it is, and I'm going to put that in the end screen and also in the description box. If I forget, please leave a comment and I will do that. So now let us start with x0 is 1.5. That's the initial guess. So this is the program I have written here. So essentially what I do here is that I start with some values. Of course, I need the value of x0, which is the starting value or the starting guess. I also need something like a maximum number of iterations the code is going to do, that I call nmax, and that is some small number I use here which is going to dictate my conversion. So I'm going to call it error. Now what I do is I say xk is x0 because x0 is the initial guess. So I start off the algorithm by making this declaration. Then I do I is 1 to n max, and I have n do here. So this basically will go through the do loop until the max number I have specified that is reached. Now, so what I do is I first calculate the function value. So I'm calling it fxk. That's simply 3 to the power x minus x to the power 9. So you see here 3 to the power x minus x to the power 9. Remember, this double star is exponentiation in Fortran. Now I put the derivative here, that is dfxk, that is this value here. So 3 to the power x into log 3 minus 9 into xk to the power 8. Now here what I have done is I have put the numbers as 9.0, 3.0, 8.0 to make sure the compiler knows I'm dealing with float here, floating point. And also you of course know that a log is the natural log, so ln is the natural log here. Now the next thing I do is I calculate this ratio fxk by f dash xk, and I call this delta. Now I need some way to escape out of this particular loop in case I have already converged. So what I do is I create a value out of this particular value. So I create this if statement that if abs delta is less than this small number I have specified, then you can exit the do loop. So this statement is very useful. It lets me escape the do loop in case I have converged. And I have to use the absolute value here because this number can go positive or negative. Of course, you know that in the end, as you reach toward the solution, fxk is going to become almost 0 or 0 because that's the value of the equation. And so at the solution point, fx is 0 by definition of the root. So in case you of course converge, you will leave this system, but if you don't, you calculate xk1 is xk minus delta, which is this equation here written in the form that xk plus 1 is here. So I'm calling it xk1, xk is xk, and minus delta, delta being this particular value fxk by f dash xk, which we have obtained here. And then I'm just printing the values of I, xk, and xk1. And finally, the last step I must remember is to put this xk1 value into xk because that's going to be used in the next round. So this is the step where you go from x0 to x1, from x1 to x2, from x2 to x3, and so on. And then of course I end the do loop, and finally I print out that xk1, whatever comes out of the do loop here, is the solution. So I took this particular program and I copied and pasted it in the compiler here, and I have run it with the values of n max is 10, x0 is 1.5, and the small number is 0.00001, so up to fifth decimal place. And so you can see that I start off with 1.5. The first iteration I get 1.35 something, then I use that as the starting value 1.35, I get to 1.24, from 1.24 I get to 1.17, I continue all this way and I get finally 1.1508 is the solution. So that's printed out here, is that 1.1508 is the solution. And generally Newton Raphson will always converge very fast because it is using derivative information, and whenever you use derivative information the algorithms work very fast because you actually know the instantaneous slope of the equation concerned. Now in Math Question Bank 5, I have done this problem in Excel. You can do it in Microsoft Excel also. Microsoft Excel is actually quite powerful. Many people don't know about it, but you can do numerical calculations there. And there also the solution was obtained to be 1.1508. If you are interested in the exact solution of this equation, check out Math Question Bank 5 for the solution using the Lambert W function. So that was the lecture for today, and you got introduced to do loops and how to use it in realistic numerical programming, like solving the typical equation using methods such as Newton Raphson. Now, as a homework problem, I'll like you to write a program to solve the same equation but use the secant method. And if you use the secant method, you actually do not need to use the derivative, that is, you do not need f dash x. Instead, you use this approximation here. Again, if you are interested, the formula I have derived in Math Question Bank 5. And now you are going to need two initial guesses. So x0 and x1 is going to be required. Those you can take as 1 and 1.5 just to set the algorithm moving. And of course, you can see from this particular formula that if you give x0 and x1, you are going to get x2, and then you can start off the algorithm and work till you converge. So that's of course the aim in all numerical methods. So this was the tutorial for today. Of course, you know that the do and do statement is something which is quite easy to use and which we typically try to use in Fortran. Now, when I was writing my first programs, of course, the do continue statement was the way to go, and there were all these numerical identifiers which used to be put out in Fortran code. So you would have various numbers 10, 20, 30, whatever the person came up with. And by using the undo, that particular process was removed. So we do not need those numbers anymore in most cases. So I'll end this video now and I will see you in my next lecture where we are going to talk about the dimensional statements, which are going to introduce you to how to use vectors, matrices, and tensors in Fortran.